Hey there, welcome back to Short Text 331. Today we're going to talk about roots using the fixed point method. And as you recall, last time in the previous video, we talked about the Newton-Raphson method, a way to calculate roots or to refine our knowledge of a root. And so today we're going to talk about a related method that's called the fixed point method. With Newton-Raphson, we had an equation, a fundamental equation that looked like this. So we defined a new approximation to our root given by our old approximation or our starting point minus the function evaluated at that point divided by the derivative of the function evaluated at that point. And of course, we had to be careful that this derivative was not too close to zero, certainly not exactly zero, otherwise this would blow up. And the situation we want to be in is a situation where this is a small correction. So we want to sort of have an idea of where the root is, and then we want to start correcting it by iterating on this equation. So this is our first approximation. We subtract this quantity, we get a new estimate, and then we insert that into this equation again, and we iterate on that until the new result is approximately equal to the old one, up to some required precision. And at that point, we stop, or we can stop after a fixed number of iterations if that's what we want to do. So the idea of the fixed point method is actually very similar. So our equation to find a root, of course, is always something that looks like this, f of x equal to 0. And our first job, is to replace that by a problem of this form. And there'll be more than one way to do that. So we want to rewrite this problem as x equals to g of x for some g of x. And there'll be many ways to do that. And here's an example, a very, very simple example. Suppose we want to find the solutions to this equation. So the roots of this problem, x squared plus x minus cosine x equal to 0. So this is our f of x. So this is right now in the form f of x equal to 0. But we want to write it as x equals to g of x. So one thing we can do is we can put the cosine on the other side of the equation and the x squared on the other side of the equation. We're free to do that. And so then our problem has been rewritten as x equals g of x, where this is our g of x. But we could have chosen to put all this on the other side of the equation and then take the square root and define g of x in this way. G of x given by plus or minus the square root of cosine of x minus x. You could also add and subtract x, or if you want, add x on both sides of the equation, and so you have x equals to x squared plus 2x minus cosine x. That's also allowed, and it will define yet another g of x. The key point is that no matter what you choose for g of x, you have to have this condition, that the derivative of g of x in magnitude is less than 1. This is what's called a Lipschitz type condition, and is what you need for the method to converge. This will define a region for x, for the values of x, where you can apply the method, and you need your root to be in that region as well as your starting point. So if your starting point is not in a region, then the mapping generated by g of x will take you away from the region, and who knows where you might land with your next point. So you must have then that your x0, your starting point, is in that region where the magnitude of the derivative of g is less than 1. And then you want to make sure that your root is also in that region. So as I was saying also in the previous video and at the beginning of this one, you sort of need to have an idea of where the root is. These methods are not methods that will be smart and find you all the roots of a function. They're methods to calculate or refine the knowledge of a root where you sort of already know where it is. Now, once you have all that and you have an understanding of your function g of x and its derivative and so on, then you can proceed. And the way to proceed is actually very simple. So you pick your initial x0, you calculate g of x0, and you set x1, so your next point, equals to that g of x0. And then you return to the beginning, where now this role of x0 is played by x1. In other words, you iterate on this equation. x1 equals to g of x0, x2 is equal to g of x1, x3 equals g of x2, and so on and so forth. And as the process converges, we approach x equals to g of x. So that's really all there is. You iterate on this equation, and when you converge, then by definition, you will have approached a solution, because we simply rewrote our problem f of x equals 0 as x equals g of x. And so when we reach x equals g of x, then we have approached the solution. So geometrically, the situation looks sort of like this. Imagine that in red here, we have plotted our function y equals g of x. In green, we have y equals to x. That's the other geometric piece that we need. And this is our starting point, x0. So we go up, and this is where we find g of x0, where x0 here intersects g of x. And now we draw a horizontal line, in this case it's going to be to the right, until we find y equals x. Because at that point, if we draw a line downwards like this, then we're going to find x1. Because this is the point this is the line y equals x. And so g of x0 being equal to y equals x here means that if we draw a line downwards here, we're going to find x1, because x1 is by definition equals to g of x0. And so that's how we find it. This is, by the way, the location of the root where y equals x intersects y equals g of x. And so that's the point here. That's our target point. But now we have an x1. And so we go to the next plot here and we start the same process. x1, we draw where we find g of x1. That's this point right here. And we draw horizontally now to the left, it turns out, up to y equals x. And then downwards to find x2. So that's the location of x2. So you see we're approaching the root here in this construction that I made, in this geometric construction for this random function y equals g of x that I drew here. I have no knowledge exactly what this is. I just drew it sort of improvising what that might look like geometrically. Now, in this process, to draw this, always what you need to do is you go from the x-axis to g of x. So suppose we have x1 here. This is our point x1 on the x-axis up to g of x. And then in this case, we go to the left, but it might have been to the right. Then you go from g of x to y equals to x. So that's the next leg here. You go to y equals g of x, and then downwards to the x-axis again. And that's how you find the x2 point. So notice that's exactly what we did here. We went from the x-axis to g of x, from g of x to y equals x, and then downwards again to the x-axis. Once you have those things, then you repeat the process on and on and on. And you go from x0 to x1, and then here from x1 to x2, and you can go again from x2, you go up to g of x, from g of x to y equals x, and then you go downwards to the x-axis and you find your next x3, and so on and so forth. And that's how you will approach the solution, assuming that the magnitude of the derivative of g of x is less than 1, and that your starting point was in that region, and so then you will converge. So note that the Newton-Raphson method is actually a type of fixed point method. But in that case, there's a very specific g of x. So in that case, g of x is x minus f of x divided by f prime of x. And so in that case, our convergence criterion, that the derivative of g of x, which is all this, has to be in magnitude less than 1, gives us this more complicated expression in terms of f. So f of x times f double prime of x, so the second derivative have to be divided by f prime of x squared, and then that whole quantity has to be in magnitude less than 1. So you can derive this very easily by taking derivatives of actually just one derivative of g of x. And that is, of course, under the assumption that this f prime of x is our fundamental quantity that cannot be close to 0, and that we can neglect the second derivative versus the first derivative, and so on, as we saw in the previous video. So there may be situations where that's not true. So we're assuming, when using Newton-Raphson, that the approach to the root is linear. But what if it's not linear? What if the approach to the root is quadratic or cubic or something else? Then you have to modify the method a little bit like we discussed in the previous video. So then this convergence criterion will be modified as well. So you can think about that. So first derive it for the simple case of linear approach that you have here, but then you can wonder and you can try to answer the question, how does this change when the root approach is not linear? And that's it. That's all I have for you today. This is a very, very brief reminder of what the fixed point method is and how it's related to Newton-Raphson and convergence criteria. I hope you find this video useful. As always, if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com. You can leave a comment in the comment section below. And as always, if you find these videos useful, please consider liking and subscribing to the channel. And I'll see you next time.